కొత్త వైరస్ అనిగా యుగం అయిపోతుందేమో, కలియుగం ఏమన్నా.
అంటే అంతకుముందు కూడా చాలా మంది పెడతారు, 10% 20% మనకు జనం అవుతాయి. ఈసారి జరగకుండా మనం ఏదో ముందు ఇంట్లో వదలుతాం.
వచ్చినారు 8 members.
పొద్దున పర్లేదు, కంటిన్యూస్ 40 పైన నువ్వు ఫీడ్బ్యాక్ ఫామ్ పెట్టినా కూడా 40 పైన ఉన్నారు. నేను 4
నమస్కారం సార్, కాలేజీకి వస్తున్నారు సార్?
ఏమో సార్, మన పర్మిట్ వచ్చి
సార్ శర్మ సార్
వచ్చే కదా కాలేజీ
అదే కదా. నేనైతే
ఏం మాట్లాడలే. ఇన్వైట్ చేస్తున్నాను లాస్ట్.
ఓకే వెడ్నెస్డే కదా? ఓకే 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 ఓకే
కాదు
నా జైలులో గొప్ప కూడా తెలుసు.
ఈయన సార్ ఎక్కడున్నాడు? ఎక్కడున్నాడు? చెప్పమ్మా.
నా ఫ్రెండ్స్ అక్కడ క్లాస్మేట్స్.
పూజ ఎగ్జామ్ ఉందా? మరి ఛాన్స్ ట్రై చేసిన ఈరోజు ఎగ్జామ్ లేదా? సార్ తిన్నావా? సరే సరే సరే. ఇంకేమ్మా? ఇప్పుడే అయిపోయింది. తినేటప్పుడు నీకు ఫోన్ చేసుకుని ఎత్తలేదు. తినేటప్పుడే నీకు ఫోన్ చేసి ఎత్తలేదు నువ్వు. చెప్పమ్మా. ఆ. సరే సరే. హలో హలో హలో, సిగ్నల్ కటింగ్, మళ్ళీ చేస్తానే. నువ్వు ఇట్లా అడిగి వచ్చేట్లంటే నన్ను అడగాకు, నాకేమొచ్చిందని నువ్వు అడుగుతున్నావు. మరి పెట్టయితే చూస్తాలే, అది పెట్టమ్మా, నేను చూసా. ఓకే ఓకే, బాయ్. పెట్టమ్మా, పెట్టు 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 పెట్టు. ఫస్ట్ సార్ ఒప్పుకున్నాడు. తర్వాత అప్పుడు వీసీ వెంకటరామరెడ్డి ఉండే. ఎందుకు లేదా రామరెడ్డి అయితే బెటర్ కదా నీకు, ఎంటెక్ అది ఎంటెక్ అయ్యే కదా, మళ్ళీ ఎందుకు మార్చుకుంటాం అని ఈయన సార్ అసలు ఇన్ ప్రిన్సిపల్ యాక్సెప్టెడ్. సరే చూస్తున్నాం అంటే నేను ఇచ్చినప్పుడు చేయలేదు సార్ అంటే. అన్మిట్ ఏంటది సార్? సార్ 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 గుడ్ ఈవినింగ్ సార్. శర్మ సార్, తిరుపతి రెడ్డి సార్, ఆర్జిఎం కాలేజ్ నుంచి మాట్లాడుతున్నాను సార్.
బాగున్నారా
సార్? సార్ బాగున్నారు సార్, బాగున్నారు సార్.
వెరీ నైస్
సార్, నేను మీ శిష్యుడిని సార్. 2099 సార్, 99 సార్.
అవును,
రామరెడ్డి సార్ దగ్గర పిహెచ్డి అయింది సార్.
అవునా?
యాక్చువల్ గా మీ దగ్గర మీరు అప్పుడు మీరు ఎంటెక్ రామరెడ్డి సారే ఉన్నాడు.
అవును,
పిహెచ్డి కూడా సార్ దగ్గరే సార్. 2003 లో చేశాను,
వెరీ
7 లో అయిపోయింది సార్.
వెరీ గుడ్, వెరీ
బాగున్నారు సార్, మేడం అంతా
అందరూ బాగున్నారండి.
ఇప్పుడు ఎక్కడ సార్? హైదరాబాద్ ఉన్నారు సార్.
హైదరాబాద్.
ఆయన సార్ కిషన్ కుమార్ రెడ్డి సార్. సార్
ఆయన కొద్ది కాలం గుజరాత్ లో చేశారు.
అవునవును సార్.
చేసి మళ్ళీ వెనక్కి వచ్చేసారు.
ఓకే. ఇప్పుడు ఎవరు ఇక్కడ? గుప్తా
మల్లారెడ్డిలో సమ్ యాక్టివిటీలో ఉన్నారు. మల్లారెడ్డి.
ఓకే ఓకే సార్, బాగున్నారు సార్. హెల్త్ అంతా బాగుంది సార్?
అంత బాగా.
మీ శిష్యులందరూ ఇప్పుడు అశోక్ ఇక్కడ ఉన్నారు సార్, ఇక్కడ ఎన్బికేఆర్ లో. ఆయన కూడా పిహెచ్డి అయిపోయింది.
ఓకే.
మన 99 బ్యాచ్ అంతా అయిపోయింది సార్ ఆల్మోస్ట్. అందరూ ఉన్నారు. అందరు 2-3 ప్రిన్సిపాల్స్ గా ఉన్నారు మీ శిష్యులు, మన బ్యాచ్ అంతా.
వెరీ గుడ్
సార్. బాగున్నారు కదా సార్?
అంత ఫైన్ అండి.
ఓకే సార్. ఓకే సార్. రైట్ సార్, థ్యాంక్ యూ సార్.
ఓకే.
మూడో క్లాస్ నా కోడ్ టెస్ట్ ఉంటే నా క్లాస్ అయితే 3 అవర్స్ వచ్చి బయటకు వచ్చేస్తుంది. ఈరోజు మళ్ళీ పోవాలి, స్టూడెంట్ ఉంది, మళ్ళీ స్టూడెంట్ పోవాలి, మళ్ళీ అర్థం కాల.
So good afternoon to everyone. So I welcome you all for the afternoon session on renewable energy intervention in industry, domestic and commercial applications. So today we have Dr. K.V. Sharma sir, so Professor of Mechanical Engineering, JNTU, Hyderabad. So before starting the session, I would like to introduce the Professor K.V. Sharma sir. So Sharma sir is from Center for Energy Studies, Department of Mechanical Engineering, JNTU, Hyderabad. So sir did PhD in the year 2000 from the JNTU University, Hyderabad, and a Master of Engineering in the year 1988 from the Andhra University College, Visakhapatnam. Graduated in the year 1982 from JNTU College of Engineering, Anantapur. So sir has the vast teaching experience in various centers. And the research experience, worked as a research assistant under the Departmental Research Support Program, Department of Mechanical Engineering, funded by UGC, New Delhi, at AU College of Engineering, Visakhapatnam. So, sir handled many subjects, including renewable energy sources, and sir also taught the subjects in the Malaysian universities also. So, sir is an active member in the development activities in the department, mechanical department. So, in the formation of syllabus, course revision, and proposed a new course on aerospace propulsion, fabrication of experimental setups. SAR is also associated with the professional bodies like Fellow, Institution of Engineers India, Life Member, Indian Society for Heat and Mass Transfer, Life Member, High Energy Materials Research Society of India, Life Member, Indian Society for Technical Education, Life Member, Solar Energy Society of India. And also, sir is actively participated in academic activities. So, university committee to examine journals from private colleges for UGC approval, nominated to Academic Council of CVR College of Engineering for 2 years, nominated as member, Board of Studies of Aeronautical Engineering of Guru Nanak Institute of Technical Campus and Institute of Aeronautical Engineering for 2 years, nominated as member, Board of Studies of Mechanical Engineering of CMR Institute of Technology and Institute of Aeronautical Engineering for 2 years, member doctoral committee of PhD student at the School of Mechanical Engineering, Vellore Institute of Technology, that is deemed university, doctoral students thesis evaluation of Gandhi Gram Rural Institute, National Institute of Technology, Durgapur, master students dissertation, University of Pretoria, evaluation of project proposals from Qatar National Research Fund, evaluation of project proposal from University Technology Petronas, evaluation of project proposals from National Science Center of Poland, member of the Board of Studies in Nano Science and Technology, Institute of Science and Technology, JNTU Hyderabad, member of UG PG Board of Studies in Mechanical Engineering, Pondicherry Engineering College, University of Pondicherry, member of the Board of Studies in Mechanical Engineering, G Polarity Engineering College, Kurnool. So, Chairman, Board of Studies in Energy Systems, JNTU College of Engineering. And also, sir held many administrative responsibilities. Chairman of committee to establish a solar power plant in the campus of Jawaharlal Nehru Technological University, Hyderabad. Member of the committee to review the revised guidelines for undertaking industrial consultancy activity in the JNTU University, Hyderabad. Nominated to governing body of Mother Teresa College of Engineering and Technology, Karimnagar district. Head coordinator, Center for Energy Studies, JNTU College of Engineering, Hyderabad. Expert member, recruitment of faculty for private engineering college affiliated to JNTU. Chairman, evaluation committee for starting new colleges under All India Council of Technical Education, New Delhi. Internal member, University Purchase Committee, Nano Science and Technology, JNTU Hyderabad. Member, National Advisory Committee of Center for Energy, Jawaharlal Nehru Institute of Advanced Studies, Dr. D. Swaminathan Research Foundation, Hyderabad. Chairman, Organizing Secretary, ISHMT, ASME International HMT Conference, and Student Training and Placement Officer. So, sir held many positions and completed under the supervision of Sharma sir, 22 PhD completed, and sir published around 112 international publications and 93 international and national conferences. Sir published 8 book chapters and product recognition and awards to the account of Sharma sir, 8 patents obtained 1, award received for research publication 1, project consultancy undertaken 15. So, sir is having the vast experience in the renewable energy. So, sir is going to share valuable information in this session. Thank you, sir, for accepting our invitation. So, to give the expert talk in renewable energy intervention in solar and renewable domestic and commercial applications. So, I welcome you, sir, once again. So, thank you, sir, and over to you, sir.
Thank you. Thank you very much for your good words about me. So without any further delay, I would like to start my presentation. Is it visible?
Yes, sir, visible.
So today I would like to present on some of the activities that has been done under my guidance in the area of solar thermal energy conversion. I would like to stress on this flat plate collectors, mainly on flat plate collectors, so that any further research can be done. So the ideas in this area can be shared for any upcoming faculty or student project works. I will just dwell upon evacuated tube collectors about the brief Indian energy scenario. Then I will be going to what is called the parametric analysis of flat plate collectors. It's a numerical approach. So a program has been written and then we try to estimate various parameters involving the efficiency of a flat plate collector. So then we identify what is that we have to do in order to enhance the efficiency of a flat plate collector. So this will be taken as a problem. So this can also be extended further for an evacuated tube collector by students or staff. So after identification of the parameters, we go in for what is called the properties of certain fluids, which we refer to as nanofluid. So we apply this characteristic fluid for free convection or for a thermosiphon flat plate collector and go into for the forced convection analysis. So what are the experiments done and how we can learn what we learn from this, which can be implemented in our laboratory classes or for further experiments. So the energy scenario of the world is something like this. The consumption pattern of the total 100, we see that the renewables constitute about 2.3%, in which we have the solar constituting only 0.2% of the world energy sources. So there is a lot of scope for the world to go in for solar, which we also know from the government of India plans to go in for more amount of the energy generation from photovoltaic panels, converting the solar energy into electricity. Coming to India, the energy installed capacity is somewhat like this. About 60% is the conventional thermal power plants. About 14% is hydro, gas constitute about 8%, and renewables constitute about 16%, of which the solar is just about 3%. So we can say that the solar energy, more amount of solar energy is being utilized in India. So the renewable from solar is about 3%, which is more than that of the world. We know what is the mechanism of energy conversion from the sun. So the basic concept is that the solar radiation falls on a simple structure, which we call it as a flat plate. The energy passes through a glass cover. It enters into a chamber where we have a surface, normally a good metallic surface, which will absorb the heat. And that heat is being transferred to the liquid which is flowing inside the tubes. We see that the radiation that is falling enters, but however, we know from the law of heat transfer that this absorber plate, when its temperature is more than that of the ambient, naturally when it absorbs solar radiation, we see that the plate temperature shoots up to about 100 degrees or so. And consequently, there is a temperature potential between the observer plate and the ambient. And so the energy is being lost by the mechanisms called convection and radiation. However, the glass plate prevents that. And so there is a multiple reflection taking place so that more amount of energy is absorbed by the plate and less amount of energy is radiated back into the atmosphere. So this is an effective means by which we try to convert the solar radiation into useful form. So the characteristics of the glass plate and the observer plate are important for us. We know a property called the transmittivity of the glass plate to be as high as about 92%. So this is obtained by minimizing the iron content in the glass. So when we are able to control the iron content in glass, it becomes what is called, we call it as selective transmitting surface, a quality by which the long wavelength range of wavelengths which is emanated from the observer plate is prevented by this glass plate so that the energy is trapped and it is absorbed once again due to multiple reflections. Similarly, the observer plate to which we have the tubes welded will definitely see that the more amount of energy is absorbed by the plate. This is due to the property which we once again call it as selective surface. So we have selective absorbing surface and selective transmitting surface, the qualities of which in the case of the glass, it is by preventing the radiation to go into the atmosphere. In the case of the observer plate, it is the ability to absorb higher and higher amount of energy in a wide range of wavelengths. So this is an important parameter which helps in the effective conversion of solar energy into heat. Further looking into the observer plate, if it were to be just a copper plate, we have the absorptivity to be less and emissivity is also low. However, when we go for certain special coatings on these observer surfaces, most of us must have seen a flat plate collector, and this flat plate collector is generally, when we look at it, it will be black in color. So it has, if it is coated with lacquer, its absorptivity is very high. It has gone up from 0.05 to 0.95. So the absorptivity increases very high. However, the emissivity, it also once again radiates energy back into the atmosphere, which is not advantageous to us. Now, when we go for black chrome, we have absorptivity to be very high and also emissivity is about 12%. But when we go for chemical vapor deposition or physical vapor deposition, PVD or CVD method of coating an observer surface, we see that its absorptivity is very high of the order of about 95% and emissivity is as low as 0.05. So we see that most of the flat plate collectors have such a type of coating which will help us to enhance the efficiency of a flat plate collector. We have different surfaces. We have different absorber surfaces. We call it as collector absorber surfaces because these surfaces not only collect but also transfers the energy to the working fluid flowing in these tubes. As we see, there are various designs depending upon the nature of application. If we want to have water as the working medium, or if we want to heat water, a fluid, liquid, then we may go in for such type of systems. But if we require some fluid such as air to be heated, then we may also go in for different types of systems such as this one. So as you can see here, it is the tube and the absorber plate are in line. So it can also be below the absorber plate. So there are various designs which will help us to, people have been working with such designs in order to see how best we can convert the solar radiation into useful energy. So other designs such as serpentine design for the flow of the liquid, many people have tried, or it can be something like this. This is very common, as all of you might have seen, or it can be in this form. It is formed inside the tube sheet, metal sheet, or it can be something like this, a wavy like structure, which we call it as a corrugated sheet. So there are various designs for the tube arrangements, but normally we go in for the second type. This type is very common. We have the inlet header, we have tubes rising or risers, and we have the outlet header. So this is the basic structure. In addition, we see that the flow of the working fluid can be something like this. As solar radiation falls on the collector absorber plate, which is here, so the liquid, the cold water from the bottom will go up, gets heated due to solar radiation, and as the density decreases, it goes into a chamber, which is a double wall insulated tank, and the cold fluid from the bottom will come down and then gets heated up. So if there were to be no air bubbles in between, and if it is a continuously, it is filled with completely with the liquid, without the aid of external pump, we can see due to solar radiation, the density decreases, and that vacuum or that space, we cannot call it as vacuum, that space being filled by the cold water coming from the bottom. So in this way, there is a circulation of cold water, hot water, with the aid of this system, working system. So which we normally call it as a thermosiphon effect. So most of the domestic water heating systems come under this category. So we have the cross section in this way. We have what is called the casing. We have the headers. These two headers are connected with the riser tubes, over which we have the absorber plate, and we have the glass cover. So the absorber plate can be over the riser tubes, or it can be in line with the riser tubes. Different designs we have seen. And there is a spacing between the glass cover and the absorber plate. So the spacing is one parameter that is of importance to us. So we connect it to a storage tank. Sorry. So there is a continuous flow of water in this such a system. So this is very commonly used in our this thing. At homes or in colleges, we see such systems because it is cheap. It doesn't require any external pump. It doesn't require much of maintenance. So hence we go in for a kind of a thermosiphon system. So the solar radiation which is falling, let us see how this energy gets manifested. If 100% of energy comes from the sun, so about 8% gets reflected, about 2% is absorbed by the glass cover. The glass is what we call it also as a cover. And the remaining part goes to the absorber plate, and in the absorber plate, about 60% goes for heating up of water, about 6% is reflected by the absorber plate towards the glass cover, which constitute approximately 6%. And also there is a reflection from the surface, from the absorber plate, which constitute about 8. And there are losses from the absorber plate into the ambient by the mechanisms called convection. So convection and radiation are the two mechanisms or the two modes of energy losses from a flat plate collector. The energy which is lost will be coming to the top, passes through the glass cover into the ambient, into the atmosphere. The energy can also be lost from the bottom, which constitute about 3% by conduction mechanism. A small part is also lost from the sides of the casing, which of course is not that significant. These are the major losses that has to be accounted for. So our objective in designing a flat plate collector is to see how to increase the 60%. What are the ways by which we can enhance the efficient conversion of solar radiation into useful heat? We can also think of a mechanism by which we have a pump. So this pump continuously circulates the water, and in between we also have a storage tank. So by this mechanism, there is a continuous transfer of heat. It has its own advantages and as well as limitations. If the heat absorbed by the collector absorber plate is less, still you are spending energy for circulation of water by the pump. So if the heat is high, maybe the pump flow rate is not in our control. So there are certain limitations in this, but however, when we go for large systems for water heating, this is one of the best ways by which we go for efficient transfer of energy from the absorber plate to the working medium. So there is another type which we call it as an evacuated tube collector. So an evacuated tube collector is a double glass layer. Between the two glass layers, as we have seen in the earlier figure, you see that there is a gap, and this gap is not evacuated in the case of a flat plate collector. Consequently, the convection losses in a flat plate collector is as high as 13%. However, in the case of evacuated tube, there is a glass which is between the two glass, air is extracted, or there is vacuum between the two glass covers, and consequently the convective loss will be minimized, and hence the efficiency of an evacuated tube collector will be higher than that of the flat plate collector. So how do we extract energy from an evacuated tube? This is one of the designs which is available to us. So you send in the tube, you have a tube, and this tube is located at the center of the evacuated tube. So the liquid enters here and then flows and then comes out. So solar radiation which is falling on this absorber plate to which this tube is connected will receive the heat and then it gets heated up. So it can also be by, it has to be generally by forced circulation, because water cannot enter just a tube like this with so many bends and so many glass evacuated tubes. So consequently, we have a pump which will pump the water, generally water, into these tubes and take out the heat. It looks, a set of evacuated tubes will look something like this. I think most of you must have seen. So there are a large number of evacuated tubes here, and all these tubes are connected to a storage tank. They'll be fitted to the storage tank. So the water which is inside this storage tank comes by thermosiphon effect, gets heated up, and then goes into the tank. So there is no control of liquid as in the earlier case. In the earlier case, in each and every glass tube, we have the tube coming in and going out. So that is one type of design. Also, you can have such type of a kind of a heat pipe as shown here. I think most of you are aware of what a heat pipe is. A heat pipe is a closed container wherein we have a working fluid. On one side, you have the energy being transferred, and on the other side, we call it as the evaporator section. And at the other end, we have the condenser section. So from the liquid, the working fluid inside this heat pipe gets evaporated, the liquid gets evaporated, goes to the other end. So in the condenser, it gives off the heat. So there is a continuous transfer of energy from the hot end to the cold end. In this process, the working fluid has a change of phase. So it becomes liquid, then becomes vapor. From vapor, it gets condensed, once again becomes liquid. So there is a continuous circulation of the working fluid, and thereby the energy is transferred from inside of the evacuated tube to the working fluid. So these two are two different areas. So this can be a sealed one. So the working fluid which is actually taking part in the energy transfer is different from the liquid that is flowing inside these tubes, which is used for utilities. So one more cross section, a figure which helps you to understand what it is. So once again, an expanded view, I could have shown this. So this is the working fluid. The cold fluid comes, absorbs the heat, becomes hot, transfer it to the working fluid as shown here. So there are different designs here. You can have a finned structure to this tube, to this heat pipe for efficient conversion of energy. So after all our designs are meant to see how best we can convert the solar radiation into useful energy. Another type, so we have the vacuum tube. So we have the vacuum between the two glass covers. So we have a tube which transfers it. So these are just to show you that there are large number of designs. And the difference here is that it is here you have a metallic part. As shown here, you have a metallic part, two metallic parts, so and the tubes. So that there is a transfer of energy. So this is a kind of an absorber plate and this is the tube. So transferring the basic concepts in flat plate collector to an evacuated tube. Various designs as you can see here. So to which you have the tube integral with this. So the liquid enters, takes the heat and then comes out as shown here. So there are different types of evacuated tubes. One more here. So it is a copper tube as you can see here. It can be integral, it can be different, two different pieces so that it can be handled easily. The other type of what we call it as a cylindrical parabolic concentrator, which is normally used for steam generation. Most of us must have gone to Tirupati. So there for cooking of rice, they make use of such evacuated tubes, cylindrical parabolic concentrators for the generation of steam, and that steam is utilized for the preparation of food, which is given as Annaprasadam there. So you also have, so a flat plate collector is generally fixed in orientation. However, there are other continuous tracking mechanisms in order to see that there is an efficient incident of solar radiation on the absorber plate. Normally, in the morning or at one point when the flat plate collector is inclined, there is a perpendicular direction in which the solar radiation falls on it. But however, as the sun traverses, the radiation which is falling on this absorber plate, the angle changes and hence less amount of energy is incident on it. But however, if you are able to continuously move the collector, move the flat plate collector or any solar energy conversion devices, then the energy absorption or the energy incident on the collector will be maximum. To see that it is maximum, we have to see that the collector is always, the solar radiation falls on the collector in a perpendicular direction all the time. If we are able to move it, then it is the best. So such a system is this tracking mechanism. So there are tracking mechanisms, there are algorithms which will aid in continuous tracking of the sun each and every day of the year. So in fact, we can write based on the sun-earth geometry. There are various methods of tracking it or writing a program. It is a different area which we are not further going into. There is also what is called a dish type of concentrator, which will, in fact, we can, at this point, at the focal point, we can have a cooker. So I can take such a system and keep it in the sun. At this location, I can keep a cooker so as to cook food. So that type of systems are also available in India. So you can also use it for various applications. The applications depend upon your objective. I think this is also another type wherein the solar radiation gets reflected to a particular location on a central tower so that maximum amount of energy falls on it for conversion. So the temperatures can also reach, according to studies, about 700 degrees centigrade. Now we have seen different types of collectors. We have seen initially a flat plate collector in detail. Then we have seen evacuated tube collector, which is also very common now. These are of different sizes, and hence, depending upon the size, we can design the inner absorb, whatever design, internal design we would like to. And we have seen a disc type, then concentrators of different shapes, cylindrical, parabolic concentrator, so on and so forth. However, we see that we are not able to convert 100% of solar radiation into useful thermal energy. So we see the reasons as to why we are not able to do it and try to minimize it. So that is the objective of our presentation. And we also see that the inclination to the surface, as I have stated earlier, because if we don't track the sun in a flat plate collector, naturally the solar radiation which is incident on the observer plate gets decreased. Then always the plate temperature is greater than the ambient, and hence there is a large amount of losses due to convection and radiation from the collector observer plate through the glass cover to the atmosphere. There is also a spacing between the observer plate and the glass cover. As we all have seen a flat plate collector, there is a space. However, what is the impact of losses on the spacing between the observer plate and glass cover? So what is the impact of ambient temperature on the performance of a flat plate collector? As we all know from heat transfer, as the observer plate temperature is high, and if the ambient temperature is low, as in winters, so there will be a large amount of losses due to large temperature potential. And also, the solar radiation is not a constant. In the early mornings, it starts from about, say, 100. As the time progresses, the solar radiation incident at a location increases. It may reach a maximum at around 1 o'clock or so, and then it decreases. So there is a continuous variation of solar flux, which we call it as solar insolation, falling on a flat plate collector, which varies from as low as 0 to as maximum of 1000 watt per meter square. And the maximum solar radiation, which we all know, is about 1367 watt per meter square, which can be attained if we go out of the Earth's atmosphere. Because we are having flat plate collectors on the surface of the Earth, probably we can take it as 1000 watt per meter square as the maximum heat flux. So our objective is, as we see here, the flat plate collector efficiency as shown earlier in the figure is about 60%. So it varies generally between 30 to 60%. And naturally, as engineers, we would like to see how best we can enhance this efficiency. The efficiency of evacuated tube generally lies at, generally we say it is about 80%. So still there is a certain possibility for enhancement of the efficiency of a evacuated tube collector also. For today's presentation, I would like to limit myself to the analysis of a flat plate collector. As stated, we have selective coatings on the absorber plate, which has high absorptance of about 0.95, low emittance of about 0.05. We have the option to go for a single cover, which is normally what we have it in the market, or we can also increase the number of covers to 2. The spacing between the absorber cover and the glass cover, absorber plate and the glass cover can be varied. However, the Ministry of New and Renewable Energy has given certain guidelines, which is about 2.5 or 25 mm or 2.5 cm. So if we can think of having 2 glass covers, the losses will decrease. On one side, the losses decrease, and on the other side, the solar insulation or the energy which is passing through the 2 glass covers and reaching the absorber plate decreases. So there is a trade-off between the amount of energy entering and the amount of energy leaving as losses if we were to have more number of covers. And also the gap between the absorber plate and the glass cover, it can also be varied. Tilt is another thing, or slope we call it. This also varies. In summers we would like to have it as flat as possible, as horizontal as possible. In winter we would like to have an inclination. So generally the latitude of that place determines. So depending upon the latitude, we can have about plus or minus. So if we can vary, for winter we would like to have more than the value of the latitude angle, or in summer we would like to have lower. So there is a possibility that if we change the slope of the collector, then the efficiency can also be increased. Fluid inlet temperature and also other parameters such as what is the dust. If there is dust, naturally the losses will be high, and if there is no dust, the efficiency will be high. So this is the background on which I would like to present it. And these are the various parameters. Absorber plate temperature can vary from 310 to about 300 to 390 Kelvin. Ambient temperature, as we all know, in India it varies between this. Absorber plate emissivity, we have dealt in greater detail the absorptivity and emissivity of the absorber plate. The glass cover emissivity, glass cover also has certain amount of emissivity, angle of inclination. So these are the various parameters that are possible in the design of a flat plate collector. So I would like to see that I change one parameter and see what is the effect on the other. Our objectives are very clear. There are 2 things. I have to decrease the losses and enhance the efficiency of the flat plate collector. That is the objective for all of us. So a schematic diagram once again, for if we have missed it earlier. So we have for a flat plate collector direct radiation or beam radiation and diffuse radiation from those coming from the clouds and from the atmosphere. It enters into the flat plate collector and we have the net heat available. There are certain amount of losses by convection, by radiation. So this is the program that has been written in Fortran. So the basic energy balance is between, if there are any questions, you can ask me at the end. You can make a note of the area and then you can ask me So the basic energy balance, it is quite simple. The useful energy is equal to the amount of energy absorbed by the plate minus those of the losses. So if I can minimize the losses, I can enhance the useful energy and consequently the efficiency of the system. So that is the objective, and this we observe. So in mathematics, those of you who are working in solar renewable energy, we have this from the book Heat Transfer, a fundamental approach by Professor S.P. Sukatme of Bombay IIT. So these are the various top losses, bottom losses, and side losses. The total losses is equated. So without going much into this, I would like to dwell upon the results from the numerical program that we have. So we have what is called due to wind. There is what is called the wind heat transfer coefficient. I have varied the wind heat transfer coefficient between these two, and I have the glass emissivity as shown earlier to be I have kept it constant. The plate emissivity is 0.5. That means it is a very efficient system, a very good value. The slope beta is 20 degrees. The number of glass covers is 1. The ambient temperature is 300 Kelvin. Since we are dealing with radiation, I have the temperature always in absolute temperature scale. I have varied the glass plate temperature. If the distance between the absorber plate and the glass cover is 0.025, the glass cover temperature, I varied the plate temperature. I am able to get the glass cover temperature by running the program. We see that if I have the space to be 22.5 centimeters, it is lower as compared to 5 centimeters. It is once again a similar one. I have the glass absorber plate temperature here and the glass cover temperature here. So the absorber plate temperature will always be higher than that of the glass cover temperature. I have shown it for two emissivities here. If the emissivity is 0.1 and if the emissivity is 0.2. Naturally, if the emissivity is low, the losses from the top, which we call it as the top loss coefficient, is very low. Generally, the loss coefficient is varying from about 3 to 3.5. So when the spacing between the absorber plate and the glass cover is, all these are constants and these are variables. Top loss coefficient, when I change the tilt angle. So the tilt angle, as we all know, at equator it will be 0, and we are about 7 degrees. Kanyakumari is about 7 degrees north. So we may be at around 10, 15 or so, 17 for Hyderabad. So about 20 degrees if you take, the loss coefficient is high. But if you go towards the north and towards the loss coefficient decreases. However, there is no significant decrease. There is a decrease, but not that high. But however, if the plate temperature varies, if the plate temperature is low, the top loss coefficient is low. If the plate temperature is high, the potential between the plate and the ambient increases, and consequently the losses also increases. So this is one more. So plate temperature between the cover to glass heat transfer coefficient, or we call it as the convective heat transfer coefficient between the absorber plate and the glass cover. As we see here, as the plate temperature increases, the losses increases significantly. So this is one of the, normally when we conduct an experiment, it is not possible for us to analyze all the parameters. But if we were to go in for a numerical analysis like what I have done, it will be easy for us to know which parameters are important and which contributes significantly in the losses. Here, I'm not able to. So here I'm effect of emissivity. I don't know whether you are able to see it. So like this, we do a large number of parameters. Here, the emissivity of the plate. If the emissivity varies from 0.1 to 0.9, we see that the top loss coefficient is increasing from 3.5 to 6. Almost it is coming towards the double. So this is, and what is the impact of the plate emissivity on the top loss coefficient? Now, when I do a particular analysis, so it is quite evident that whether my program is correct or not. I am getting some results, but I do not know whether my program is reflecting the true nature of a collector. So for which I have taken the experimental data of one of the authors available in the literature, and I see that when I vary the flat plate collector emissivity, the plate emissivity between 0.05 for this one and 0.1, I see that the experimental data of some other author is in good agreement with my numerical results. So this gives me confidence that the results which I am presenting is correct. And as the emissivity increases, the top loss coefficient also increases. So from this figure, we see that the top loss coefficient can vary from about 2.5 to about 5.67, depending upon the nature, how the system is. So I have taken now here, if I change the spacing between the glass covers, if I increase the spacing from 0.025 to 0.05, or from 2.5 centimeters to 5 centimeters, I see that the loss coefficient is increasing significantly. It goes up to 17. So the top loss of the heat transfer coefficient, when it increases, it means the losses are going to increase significantly. So that is why in the Indian standards, we have about 2.5 centimeters should be the spacing between the observer plate and the glass cover. Then normally this loss coefficient, the heat transfer coefficients are interesting from the point of view of heat transfer people. But from the efficiency of a collector as a system, we can say that the efficiency graphs are now shown to you. When I change the heat flux from about 300 to 1200, which is the maximum, I cannot go more than 1200, we see that the efficiency curves, when the plate temperature is 338, when the plate temperature is high, the efficiency is low. When the plate temperature is lower, the efficiency is higher. If the plate temperature is lower, the losses will come down and hence the efficiency increases. Here also I have the effect of ambient temperature on the performance. Then once again, with the tilt angle, how the efficiency varies. As we have seen earlier, the effect of tilt angle is not that significant. However, when the heat flux changes, when the heat flux increases, the efficiency is found to increase. Once again, the emissivity of the observer plate. If the emissivity is for different emissivities I have plotted, when I change the glass temperature, on the top we have the glass. If the glass temperature is low, the efficiency is high. If the glass temperature is high, the efficiency is coming down. And this is how it is varying for different emissivities of the observer plate. Ultimately, I come to this important figure. Till now, I have done what we call it as a parametric analysis, changing different parameters associated with the functioning of a flat plate collector. And we have seen what are the major parameters influencing the efficiency. And finally, I come to this figure wherein I have changed the plate temperature for different plate temperature, or when the plate temperature increases, the efficiency decreases rapidly. So why is the plate temperature increasing? It is increasing because we are not able to extract. If we don't extract the energy absorbed by the observer plate and transfer it to the working fluid water, then naturally the plate temperature increases. So how to reduce the plate temperature or the observer plate temperature in a flat plate collector? So that is the objective with which we will try to move into the second part of our discussion, which we call it as the nanofluids. Normally, the working fluids that we use are that of water. Water is, as we know, mostly it is cheap. It is which is commonly used to extract heat. And in certain applications, we also have ethylene glycol, engine oil, so on and so forth, depending upon the nature of application. These are used to extract heat or transfer heat from one surface to another. So nanofluids are metal particles or metal oxide particles which are dispersed in liquids such as water, ethylene glycol, engine oil, and any other fluid, any other commercial thermic fluids or heat transfer fluids. So when we disperse them into these fluids and see that they are uniformly dispersed without agglomeration, without sedimentation, then these fluids are found to have enhanced thermal properties. The properties that are of interest to us here with respect to the functioning of a flat plate collector are 4 in number. They are density, specific heat, viscosity, and thermal conductivity of the base fluid such as water. And when I disperse the particle, I call it as nanofluids. So for base fluids and nanofluids, these 4 properties of the fluid are to be determined. Many people have worked on that right from about 1993. One person in the US has initiated this activity, and from the year 2003 onwards, a large number of people have started showing interest on this. After all, what is that we want? We want efficient conversion of energy, isn't it? So for which this is one of the passive methods by which we can convert it into useful energy. These particles, oxide or metal particles, are of the size nanometer. Nanometer is 10 raised to the power of -9 meters. So they are of very small size, and because of their small size and being normally these oxides and metals have higher thermal conductivity when compared to the liquids, and hence when we disperse them in an efficient manner, the properties are found to enhance. The thermal conductivity is found to increase, and the increase is not linear, it can also be non-linear. So finding the advantages of these fluids, people have started making use of nanofluids, the properties being useful for efficient transfer of heat energy. So mostly people have worked with these fluids, and the amount of particles that we mix with the base liquid is generally observed to be less than 4%. We don't go for high concentrations, we go for low concentrations. Even 4% is considered to be high. So I have given the maximum concentration. But if you are interested to know the characteristics of the fluid, after more than 4%, the liquid becomes non-Newtonian. It will lose the Newtonian properties, and hence we generally limit it to 4%. So heat transfer coefficients are observed to increase. If heat transfer coefficient increases, it means it is able to extract more heat in the case of a flat plate collector. Additionally, there is no significant increase in pressure drop, or the pumping power is not that high when we compare it with the base liquid, that is water. So various people have done it, and these are some of the properties that we can make use of. For today's presentation, I would like to dwell upon basically TiO2, titanium, and silica. These are the 2 nanoparticles with which these people have worked with, and they have given the properties. So we go for what is called SEM, scanning electron microscope, will give you the shape and size of the particles in this way. This is the machine. It costs about 2 to 3 crores depending upon sorry. So this one is of TiO2 and this one is of SiO2. SiO2 silica to get the image is difficult, and hence we have in this manner. When you disperse it in different concentrations, the nanofluids look like this. If the particle size is small, of the order of about 13 nanometers, the dispersion will be quite very clear. It won't get sedimented and it will be uniformly dispersed and it will look something like this. This is Al2O3. It looks in this manner. The particles are spherical in shape. The properties of water from our data book, we can get these equations for the base liquid water. When we go for nanofluid, we have what is called the mixer relation for the estimation of nanofluid density and nanofluid specific heat. So using these two relations, we can estimate the properties, nanofluid properties, density and specific heat. But however, when we come to that of the thermal conductivity of nanofluids, we have to conduct a large number of experiments. Various people have given they have conducted experiments and they have presented the properties in journals. 1 minute, please. Yes. Any question being asked? Okay. So I have taken a large amount of data which has been presented by various authors working with different materials, different particle sizes, different operating temperatures, different concentrations. So I can vary the concentration, I can vary the temperature, I can vary the particle size, I can vary the material. So there are 4 parameters involved when we try to determine the thermal conductivity. As shown in this equation, concentration, temperature of the fluid, particle size, and material. So concentration, as concentration increases, thermal conductivity increases. As temperature increases, thermal conductivity increases. As particle size increases, thermal conductivity decreases. So that is, we can understand the physics of the problem by looking at the constants that we have developed. And if the thermal diffusivity of the particle, all of you are aware that thermal diffusivity is K by rho Cp of the particle to that of the base liquid water, as this value increases, the thermal conductivity increases. This increases for metals. So for metals, it will be higher. For oxides, it will be lower. So that also is getting reflected. So this equation can be used to determine the thermal conductivity of a nanofluid. This data has been regressed. So whenever we have such equations, it is an approximate equation. It will work within certain range of parameters. And all the data has been spread. So in this way, I can say that this equation is relatively good. I have made use of the viscometer, Brookfield viscometer, and determined the viscosity. And that data of large number of people has been subjected to regression. Once again, as the concentration increases, viscosity increases. As we all know that concentration is proportional to the amount of particles in the nanoparticles in the liquid. So as it increases, viscosity increases. As the temperature increases, viscosity decreases. We know that the viscosity decreases with temperature. Rightly, the negative sign reflects that one. So I can say that this equation reflects the true nature of the viscosity. And if the particle size increases, the viscosity decreases. So for a particular concentration, if the particle size increases, the number of particles will be lower and hence viscosity decreases. And here, this equation is valid for all nanoparticles, nanofluids. C has a value of 1, but only for SiC, silicon carbide, it is found to be 1.4. So please note that this equation can be used only for water-based nanofluids, not for all. So once again, checking the reliability of the equation, which we call it as the parity graph, same axis on the x and y for the same scale. When we plot it, we see that the deviation is within about 10%. Now I have now with me all the properties that are required. Making use of the properties, I determine the objective. What is the objective we have here? To know what is its impact on the surface temperature. If I were to have water, what will be the surface temperature? If I make use of a nanofluid, how will be the surface temperature? Is it going to increase? Is it going to decrease? Rightly, we can say that since the thermal conductivity of a nanofluid increases, we expect the absorber plate temperature to decrease as we have nanofluid flowing through these tubes. Let us see how much it is, what are the parameters that are dependent. Let us go in detail a bit. There are other ways also to enhance the heat flow. One is what is called a twisted tape. I have a tube through which I can allow the liquid, either water or nanofluid, to flow through. Also, I can have a twisted tape. So I have a tape, a strip on the lathe at equal intervals. I make a twist of 180 degrees. Thereby this we call it as a twisted tape. So I take this tape, insert it into the tube, by which I will be able to enhance the heat transfer coefficient. If the heat transfer coefficient increases, we know that more amount of energy is transferred to the fluid, and consequently the wall temperature can decrease. So I have the experimental setup. So there is a facility for me to remove this part and insert the twisted tape inside the tube for this length. I have a chiller, I have a storage tank, and this constitute, I have equipment to determine the pressure drop across the length of the tube, and I also have thermocouples here, and these thermocouples are all sent to a data logger. So I have a console which will show me the pressure drop, the temperatures at different locations. Also, I have a thermocouple measuring the inlet and outlet temperature. So this is an experimental setup. You can either make use of this, or in your college you should be having a double pipe heat exchanger or U-tube heat exchanger. So you can also convert such type of experiments making use of the technology. In fact, a PhD work is going on making use of a simple, we need not go for very complicated. You have to understand the physics of the problem, you have to make an energy balance and then equate it. So getting a PhD, doing experiments, only thing is you need patience, you need clarity of understanding, you need to conduct the experiment by spending a large amount of time. Then you get wonderful work wherever you are. So a schematic diagram, this is what I call it as a twisted tape, and this tape can be inserted inside here, inside the copper tube, over which I have insulation. I have this is a force convection apparatus. I need not call it a very specific. Only thing is I have temperature indicators, sophisticated instrumentation, which enhances the cost of the experimental setup. So these are the parameters. I have given 600 watts. I can control the average temperature of the fluid of the inlet and outlet to about 30 degrees with a deviation of about 1 degree centigrade. So that facility also, temperature setting, you can set the temperature and then run the experiment. So with that, I also have a data logger which will measure the surface and the fluid temperatures every 5 seconds and store the data so that I can know whether the system has come to steady state or not. So these are some of the parameters that I measure: flow rate of the working fluid, pressure drop across the length, and the temperatures, including the inlet and outlet temperature, for the estimation of energy balance. This study involves simply just 4 equations, which all of you are aware of. I am using electrical energy to heat the working fluid. I know from Newton's law of cooling that this is the energy by which I can estimate the heat transfer coefficient experimentally. I also know what is called a non-dimensional parameter called a Nusselt number, which is defined in this way. I can measure the friction factor by using the pressure drop from this equation, which we call it as Darcy's equation. So I conduct it with water and see the reliability of the experimental setup. I find that it is in good agreement with the various equations available in literature in the turbulent range of Reynolds number. For turbulent range, because I have conducted in that range, I have made use of this equation. If it were to be laminar range, naturally you have to make use of 64 by Re as the equation, depending upon the range. I have taken TaO2 titanium nanofluid. I have taken 1% concentration. For that, I find that the experimental data is lying in good agreement with that of two people. One is Don Tongsuk and the Abbasini. So these are equations which has been presented in the literature, and hence I have compared my experimental data to verify whether the data that I am getting is reliable or not. Then I try to analyze making use of the data. I have increased the concentration from 0.5 to 3%, and also I have shown the base liquid. These dark squares are that of water, and as I increase the concentration, I see that it is increasing up to 1%, but as I go for 1.5%, it has come down. Please note that I have done it, all these experiments at the bulk temperature or average temperature of the nanofluid is set for 30 degrees centigrade. So if the average temperature of the working fluid is 30, this is the outcome. Normally, we have a feeling that if I go on adding nanoparticles, if the concentration increases, oh, my heat transfer will be going on increasing. No, it is not the case. It also depends upon the working fluid temperature. In this case, at 30 degrees, you see that 1% concentration of TaO2 has given higher or the maximum heat transfer when compared to higher concentration of 2, 3, up to 3. Coming to SiO2, as we see in a similar way, when I increase it from 0.5 up to 3%, the 3% concentration, the triangles have come to be give the maximum heat transfer coefficient. So from 0.5, once again at the same temperature of 30 degrees centigrade, when I change it to SiO2, now 3%, for 3% concentration, the heat transfer coefficient is observed to be maximum. For TaO2, it is 1%. For SiO2, it is 3%. Now, when I try to have the complete set of data in a tabular form, this is for SiO2. For SiO2, 3%, when the nanofluid pH value, whether it is acidic or basic, we see that it is in the basic range. Its kinematic viscosity is observed to be so much, thermal conductivity is so much. Then under turbulent flow, it has given a maximum at 5. A 5 is we call it as property enhancement ratio. For turbulent flow, if the value of the property enhancement ratio defined as the enhancement in viscosity ratio to enhancement in thermal conductivity ratio, if it is less than 5, the enhancements in heat transfer take place. But if it is more than 5 enhancements, it is not advantageous for us to go for higher concentrations more than that. When it depends upon the working temperature of the fluid. In this case, it is 30. So some more plots for 0.5%, showing the same thing in a comparative manner. For 0.5% concentration, I have now shown for TaO2 and SiO2. So when I go for 1%, it is like this. TaO2 has come to a maximum, whereas SiO2 is still trying to go up. But when I go for 2%, now SiO2 has come up, circles. When I come to 3%, SiO2 has reached its maximum, whereas TaO2 is very close to that of water. So that it is not advantageous always to go on adding nanoparticles or increasing the concentration just like that. We have to have a clarity as to why we are adding, when we should add, up to what conditions this heat transfer gets enhanced. Similarly, for TaO2, we see that at 1%, the TaO2 gets a maximum enhancement of about 24%, whereas SiO2 at 3% gives a maximum enhancement of 33%. Now coming to twisted tape, we know what a twisted tape looks like. All of you can manufacture twisted tapes in the workshop. Take a small aluminum strip of width equal to the inner diameter of the tube with which you are working with. So, and the thickness can be 1 mm, not more than 1 mm. And so that it is easy for you to twist it and get the twist ratios of 5. If the twist ratio is small, is less, it is something like this. If the twist ratio is large, it will be something like a flat strip, which is close to that of a plain tube flow. So when I have it, I insert it here, and once again getting the results. So I compare it with water for different twist ratios. So this is in a plain tube and this is in twisted tape. Now I go for SiO2, and the reason why I have shown this figure is that normally when we do something, we have to compare with the equations available in the literature to show the validity of our experimental data. If it doesn't come into that, then the reliability of the experimental data is questionable. So for water, after doing it and finding that it is in good agreement with two different equations, now I have the reliability in my experimental data with nanofluoride. Similarly, I conduct it for various flow rates for SiO2 at 1.5%, for different H by D ratio. So for keeping H by D of 5, for TiO2 of different concentrations, when compared to flow in a plain tube, you see for a twisted tape, the heat transfer coefficients have increased significantly. So for Nusselt number is about 140 here, but here it has crossed 240. When twist ratio has been increased to 10, so 10 means the spacing increases and consequently heat transfer coefficient decreases. So the values have come down a bit when compared to the earlier one. So in the third one, H by D is 15, it will come down. It has come to about 200. So when it goes to 93, that means I have just introduced a strip which doesn't allow the water, which doesn't help in the water to get churned, and the water just flows like that. However, there is a strip. So you have the heat transfer coefficients coming further down. So like this, we start analyzing to see how best we can reduce the temperature of a flat plate collector. So doing a similar analysis, just as we have done it for a plain tube, we can go for a twisted tape. So we find that with the twisted tape, we see that 76% for TiO2 1%, it is 76% for 1% concentration. With the twist ratio of 5, the enhancement is 76%. However, for the same concentration, when the twist ratio is increased from 5 to 10, the enhancement has come down to 64%. Like that for 15 and 93. As you can see that the red color letters, numbers are coming down because it is becoming more and more very close to that of plain tube. For SiO2, once again, similar analysis. And taking the data and putting it in a tabular form, you see that for 3% concentration for SiO2, for H by D, you get a maximum enhancement of 98.96%. When it has increased from 5 to 10, the H by D ratio, it has decreased. So further, when we go for, we try to have the data. Now I'm confident with my data for nanofluid. I have reliable data and that data is valid. So I put it into an equation form. The equation for the estimation of Nusselt has been regressed, and you see that all the experimental data which has been done for water, TaO2 has been subjected into an equation form. If D by H, if it is a plain tube, D by H becomes 0, and hence even if it is a very high value, this has no impact, and consequently you get that value which is valid for a plain tube. Similarly, separately I have presented it for SiO2. One equation for TaO2, one for SiO2. Similarly, I would like to go for friction factor. As seen here, the friction factor is not that high as compared to that of the base liquid water. For different concentrations, maybe about 20 to 20% will be the maximum. For SiO2, it is in this manner. So one thing that you can observe is that all this data is slowly, it is coming close to that of the line Blasius equation. So this indicates that when you increase the Reynolds number, slowly it will be falling into the Blasius equation. That is, it might not, the nanofluid concentration does not have a significant impact on the pressure drop. TaO2, SiO2. Here for friction factor, I have combined that one for a wide range of Reynolds number for concentration less than 3.5, and also I have given the Prandtl numbers. Operating temperatures also may have an impact. So for that reason, I have given this equation, validity of the equation. Now I have started all this nanofluid starting with this figure. In this figure, as we have seen that when the emissivity of the plate is high, you have the efficiency coming down. So this is because as the plate temperature increases, either for 0.05, 1 or 0.95, the efficiency of a flat plate collector is coming down. So I don't want the flat plate collector temperature to shoot up. I want always to extract heat so that the plate temperature is kept as low as possible. If I want to decrease the wall temperature, I have to extract heat quickly. To extract this heat, I make use of this nanofluid, either in the forced convection mode or in the free convection mode. So people have to conduct experiments. People have been doing it. They have been showing a lot, but such a numerical analysis has not been presented till now, to the best of my knowledge. So I have now shown the surface temperatures for SiO2 and for SiO2. As you can see here, with the distance, the wall temperature is increasing. The surface temperature is increasing. However, with increase in flow rate, as the velocity is increasing, if the velocity is low, the wall temperatures are high. If the velocity of the fluid or if the flow rate is high, the wall temperatures are decreasing. The decrease in the wall temperature is from 33 to say 31. So 2 degrees centigrade decrease in temperature can be obtained as you increase the liquid flow rate from 5.8 to 15.7. This is with a concentration of SiO2 nanofluid of 1.5. So this is another way outlet temperature has also been plotted. So ultimately, I would like to say that by the use of nanofluids, you will be able to decrease the wall temperature significantly, whatever may be the flow rate, when compared to that of the base liquids such as water. The only difficulty here is that Since you are using a nanofluid, you cannot allow it to go into the mainstream. So consequently, you require a heat exchanger. So the nanofluid goes into this spiral tube in the storage tank, and once again this liquid is circulated. So the energy is transferred from the nanofluid flowing inside this tube to the useful water, or to say water, for which you wanted to heat it. So you require an indirect heating system if you are to work with a nanofluid. You can have, so people who are interested to do some experiments can work in this manner. This has been taken from ANSYS diagram, or you can go through such a YouTube type of heat exchanger for transferring the working fluid energy to, or sorry, the nanofluid, the energy associated with the nanofluid to the working fluid. So I have explained to you in detail how the energy can be utilized and how the energy losses can be reduced. You can identify what are the various parameters that influence the efficient working of a flat plate collector, which can be extended to various other types of collectors. I have explained to you how what is meant by nanofluid, and how to prepare a nanofluid has not been detailed to you, but those of you who are interested can ask me questions so that I can explain to you better. So some of the salient summary from the work that has been done is presented here. I have explained to you in detail, and these have been summarized. That earlier one, these are for the flat plate collector, the new parametric analysis. This is a summary of for nanofluids, and its flow through a plain tube as well as with twisted tape insert. These are the various references. Thank you. Now I would like to get questions from you, those of you who have some interest. Any questions with regard to your working or your interest? Because since it is an FDP, I don't want to spend more time. I would like to give you more time for interaction session.
Hello, good afternoon, sir.
Good afternoon.
Sir, very nice and excellent presentation, sir.
Thank you.
Sir, I would like to ask one small question, sir. In your work, you have used 30 nanometer size nanoparticles, sir?
No, it depends upon.
Can we go for any?
It depends upon the availability. See, Indians have limited money for projects.
Sir.
Smaller the particle size, better is the stability of the nanofluid. If you go for larger particles, the stability decreases because the viscosity of water is very low, of 1 centipoise. But if you work with high viscous fluids or with a mixture of ethylene glycol and water, you can increase the viscosity, thereby the stability is relatively enhanced.
Okay.
Right? That is one aspect of stability. Two, coming to particles, if you decrease the particle size, you can enhance the stability. Now, if you have any doubts, yes, I have worked with one particle size of 30 nanometers as shown.
That means cost will be higher, no, sir, if you go for still smaller size of nanoparticle?
It depends upon the material and the manner in which you try to address the problem. Say, for example, the nanoparticles are obtained or manufactured. You can also do the preparation. So there are different techniques available in the literature by which you yourself can prepare the nanoparticles. However, most of us have limited money, and consequently, you have to purchase chemicals. You require a lot of paraphernalia in order to prepare it. I don't know whether your chemistry lab people purchase chemicals, what is the budget and all. So normally what we do is, I don't suggest my students to prepare the nanoparticles. I ask them to purchase it. Purchasing can be from high quality to lesser quality. If you purchase it from Sigma Aldrich, the cost will be very high because they talk of 99.9% purity. But there are a large number of people who have been manufacturing nanoparticles in Bangalore, in Khammam, in various places in Tamil Nadu, so on and so forth. If you compromise on the quality, if you don't need 99.9, and if you are satisfied with 99%, with small traces of other 1 or 2 other elements, then you can have the cost quite reduced. So it all depends upon the purity of the materials that the cost is increasing. 2, if you go for graphene, the cost is very high. 5 grams will cost about 25,000 or so. But if you purchase it or if you can prepare it yourself, it will be much simpler. So it is like that.
Okay, thank you, sir.
Yes, I could not hear you.
So there are some internet connection problem.
Oh, okay.
Okay, thank you.
Thank you very much for giving me this opportunity. I thank one and all. If there are any questions, you can pose it to me. If I know, I will tell you. Otherwise, I will let you know who can address your problems. Thank you very much, Saida Reddy, for giving me this opportunity to be a part in your FDP program. I thank the college and the management for giving me this opportunity. Thank you very much.
Thank you, sir. So you have given a lot of information regarding the renewable energy for heating applications. So maybe the participants have gained a lot of knowledge in this area. So once again, thank you, sir, for sharing your valuable information. So I sent one email to you, sir. Please go through that, sir.
Some 2 questions, something like that. Am I right? Now, what is this? What is the mail regarding?
Yes.
Google Forms. Okay.
Yeah, yes.
Okay. 2 multiple questions has to be. Shall I ask the questions, or you want it to be written only?
Written.
Okay, I will send it in just.
So we will conduct at the end of the program.
Okay, I will send it.
That
Some 2 questions, multiple choice. Okay. So thank you very much. If there are no questions, I think we will call it a day.
Okay, thank you, sir.
Thank you.
Okay, dear participants, with this, today's session is over. Tomorrow, so we have the session by Bhupati, Director and Division Head, Research and Development from National Institute of Wind Energy. So all of you join tomorrow by 10:30.